Okay, welcome to another edition of the Cubicle seminar at MSRI. And I guess one usually starts these things by saying, today we have such and such from such and such university who will speak about this and that. And so today we have a great pleasure of having me speak about something, homotopy, coherent nerve, and straightening cubically. Yeah, and so I think I'm just going to start, tell you about this stuff. So I wrote some references here, and this list is more than exhaustive. It's so exhaustive that it's actually more than I will talk about. So these references, I mentioned all of them here just because they form kind of a coherent stream. So one way to do it, can you see my screen roughly, like when I'm writing? Does it work? Yeah, okay. So this paper from 2018 was kind of the first one. And based on that, we then did a special case in this paper. And so this is what I'm going to talk about today. And in 2 days, Brandon Doherty will talk about DKLS. So Brandon will show how to take these ideas to the natural conclusion, meaning, this is Wednesday. So how to describe something that looks like the Royal model structure for infinity on cubical sets. And I'm just going to say the first 2 papers are available from my website, and the third paper will be available from my website in a matter of hours. So we uploaded it to the archive yesterday, and so it's scheduled to be announced today at on Tuesday Universal Time. So yeah, even though you cannot, so you'll be able to at least see it before Brandon's talk. Okay, so I wanna start with let me tell you roughly my plan. My plan is, well, I'm gonna start with some general remarks on this category. So what happens if we take cube as the box category as the full subcategory of cat? And this is something that's done in the first of these papers, KV. But in some sense, from that point on, we're going to generalize. So then we're going to talk about the homotopy, coherent nerve, and straightening. Homotopy, coherent nerve plus straightening. That's ugly, but that's okay. And that will again follow KV. Oh, I'm making my usual mistake. So section 1, then sections 2 and 3. And finally, we're going to do straightening over the point. And for those results, straightening over the point, this, here we follow K, L, W. And I'm just going to say that here we are roughly speaking agnostic about the cube category, We're not necessarily agnostic. What I mean instead is that so there's one choice that won't work, or there are some choices that won't work. And so we should really think about it like religions. Maybe we don't want to commit to one, but we certainly know some that are not true. And so, in the third point, we're gonna have a specific choice of the cube category. And so at that point, I will reveal to you what the only true religion is. So I hope, yeah, okay. I feel like advertising it this way really doesn't oversell it. I'm going to tell you exactly which religion is true. Okay, so let's start with the assignment. So I didn't see many submissions in Gradescope, so I'm going to start by solving the exercise that I left in my talk last week. No, if you didn't submit anything on Gradescope, that's fine. So the exercise was show that if you have faces, degeneracies, connections, and diagonals, then you have a full subcategory of cat. Right? So faces, degeneracies, connections, and diagonals. And we said if you have diagonals, then you have symmetries. So now you have all the maps, and you expect to get the full subcategory. So how would you go about proving that? Well, the first observation is that we have products, and so maps from 1M to 1N are the same as, well, maps from 1M to 1 and N outside. So the only thing you need to understand is what the hell this thing is. Okay, so my claim is that I can construct all maps from cube M to just the interval using faces, degeneracies, connections, and diagonals. And so how am I going to do that? Well, I'm going to proceed by induction with respect to M. And I'm going to leave the case of M equal to 0 as an exercise, but it's not hard. And then I'm just going to tell you that if I have a function from 1 to the power of M plus 1 to 1, well, then I can define f sub t of x to be fx t. So here x represents the first m variables, and t is in the set 0, 1. Okay, and my claim is that f of xt can then be written as max f0x and then min f1x and t. And now you see that this f0 and f1 are functions of m variables, and so I really expressed the function of m plus 1 variables using just these. Okay, great. So we learned something about this. What else can we learn about this category? Well, another fact, an interesting fact, is this is a test category. And there's quite an interesting theorem that proves it. So in Maltese, so here are the book, and the title is this. So I believe it's pronounced something like "Bliblible de Bliblible Grotendijk." And so in this book, there's a theorem that tells you that a full subcategory of cat closed under products and not containing the empty category empty cat is a test category. And so, as a general theorem, that seems pretty well designed to capture exactly one example. So it's almost like a statement is designed as an exercise in maximum generality. But yeah.
Do you need some extra condition? Your full subcategory contains some category which has at least 2 objects. Otherwise, you could just take the.
Think so.
You could just take the full subcategory consisting only of the terminal category.
Oh, maybe okay. Maybe like you need to contain maybe plus extra condition, condition. But whatever the extra condition is.
Yeah. I think you may also need to have like the walking arrow or something similar to it.
Well,
yeah, exactly.
Well, not quite, because you can take non-empty finite sets, right? But I mean, by memory, you just need to have some category at least 2 objects. Is my recollection.
That doesn't disprove, like the implication doesn't go in the other direction.
No, but like having read this book, I remember that the proof that non-empty finite sets forms a test category is by the correct version of the theorem. Anyway.
Yes, I haven't read this book. I only learned how to pronounce the title. And even then, there are some bad, like I'm not perfect with that. Okay, anyway, so this is the theorem that tells you that this is a test category. And now, what do we do? Well, another thing that we can say about this category is, well, it embeds into cat. But cat embeds into another category that we really like, which is simplicial sets by the nerve factor. And on a Prishev category, you will usually have the topology given by jointly epimorphic families. Families, okay. Namely, yeah, a family of maps is a cover if like the union is epic. So so now you can take this and you can take a pre-topology on cube that's given by the restriction of this topology, and so you can ask the question, well, what happens if I take sheaves on cube with respect to this topology? And the answer is perhaps, I mean, it may be surprising at first, but if you think about it for a bit, it's not that surprising. Namely, you're going to get simplicial sets. And so that's our theorem. Okay. So how can you see that? Well, I think just as every important piece of work in algebraic geometry, you just open SGA on like at a random page and hope that there's a theorem that exactly applies to your case, and that's how you prove it. So the embedding of cube into simplicial sets gives you a map. When we take Prishev, we need to reverse directions. So we're going to have a map. So we're going to have sheaves on this category with this JF restricted to cube if we need to. And then there will be a map going this way from sheaves on simplicial sets with respect to this topology. But now this is something that we understand quite well. And this is just this is equivalent to simplicial sets. When you take sheaves with respect to the topology given by jointly epimorphic families, that on Prishev, that's just going to give you back this category. And so now I claim that this map is also an equivalence, and this is, well, I'm not going to make a fool of myself again by trying to say something in French, so I'm just going to say that this is the comparison lemma from SGA. In order to show that, all I need to show is that every representable delta n in simplicial sets can be covered by something from the cube category. Okay, so that doesn't seem too hard. Namely, what are things in the cube category? Well, these are things of the form delta 1 to the n, and then well, this quite clearly has an action of the symmetric group that permits the axis, and then we take the quotient by this action, we get this, and I would hope that you'll believe me that this is an epimorphism. So we're done proving this thing. And so what that means in particular is that I have an embedding of simplicial sets into cubical sets as embedding of sheaves into pre-sheaves, and I'm getting a left adjoint, which is the sheafification functor. And so you can ask, okay, what the hell, like, do I know that? And the answer is yes, of course you do. This is exactly the triangulation adjunction. So that is a very strong argument in favor of triangulation as your favorite functor in the world, because it is, in other words, the sheafification functor. So this is triangulation TU, whereas this is just I'm not gonna try to spell sheafification. I think this is beyond, my pay grade, as you might say, or as I started saying after watching all seasons of Bosch, which, by the way, is a great show. Highly recommend it, but the books are better. Okay, back to reality for a second now. So what is another way in which you can view this adjunction? Or what is another way in which you can view simplicial sets as a subcategory of cubical sets? Well, we can go back to what Tim said on Friday, I believe. Namely, we can ask what is, so another take on it, another take is, well, we can view, we can ask what is the Karoubi completion, the idempotent completion, Karoubi envelope of this. And the answer, as Tim told us, actually, I don't know why I wrote a question mark. Let's not do that. Well, another take on this is that these are exactly finite lattices with poset maps. And so the important thing is we don't need to preserve max and min. We only take monotone, or we take all monotone maps. There are more of those than there are of those that preserve max and min. And an easy way to see that is, well, cube is certainly a subcategory of posets. The category of posets is idempotent complete. So we just need to identify, in order to prove this fact, this is kind of a very simple fact, but what that comes down to is the following fact that you can again give to your undergraduate students as an exercise in, I don't know, combinatorics or lattice theory, if your university somehow offers a class in lattice theory, which, I don't know. So a poset P is a retract of some n, if and only if it is a lattice. So here everything is finite. So a finite poset P. Okay, great. So this is a very elementary fact, but what do I know? Well, the fundamental fact to me about idempotent completion is that I don't change the category of the category of pre-sheaves. So I get this fact out of it. But I can combine it with another fact, namely, believe it or not, but linear orders are in particular finite lattices. Oh, no up here. So this, so the inclusion like that induces, no, that's not going to be enough space. Sorry, I'm going to say a map between simplicial sets and cubical sets. And so there is I star, and it has two adjoints given by left and right Khan extensions. And now the thing to observe is that once again, if you just unwind the definitions, this is the triangulation factor. And so in particular, that gives you maybe a proof of the fact that I said below, that's really an undergraduate proof. The fact that I stated above about sheaves. So you don't need to know anything about SGA, you just need to know, let's see if I can do that. This little fact here, well, notability, you are my favorite. Yeah, you just need to know this undergraduate fact, and from that, you know that, for instance, the left adjoint in the triangulation adjunction will be preserving finite limits. Therefore, there's going to be a shiftification adjunction. Okay, so I think at that point, I'm done talking about the full subcategory. And so this is official end of part 1, end of part 1. So maybe at that point, I'll move to part 2, and I'll try to get halfway through it before we take a break, if that's okay with y'all. And so, so I'm going to say that until further notice, let's make cube an arbitrary. So arbitrary means that you absolutely must contain faces and degeneracies. So faces and degeneracies plus something, right? So without these two, like absolutely no. And then we're going to see what we need, like at each step of the constructions I'm going to be presenting. We're going to see what we need in order to perform these constructions. Okay, and so I don't know, it feels to me a little bit that we're not really being agnostic about the choice of the cube category. Because it's not that we are like not believing necessarily in any or saying we don't know. We are actually believing in all of them, right? So my friend's grandmother practices 6 different religions, I think, because she's really serious about going to heaven, but she's really unsure which religion is correct. And so just to be on the safe side, she goes to 6 different kinds of churches and does these kinds of things. So I think this is really taking Pascal's wager to its natural conclusion. Anyway, so that's what I had to say about that. So let me recall. Oh, I see a question in the chat. Do you know if the triple of adjoint functors exists for other categories of cubes other than the full subcategory? So in some cases, I think, so in some cases, I know that it doesn't. I don't know of any case where it does, well, other than the full subcategory, but there are some cases where I'm not sure, if that makes sense. But yeah, it would be good to settle that. So, okay, yeah. Okay, cool. So I'm gonna really cool. That we had this monoidal category. This was a monoidal category, and in particular, here, the tensor product is given on representables by this formula. And this is cube m plus n. And I'm just going to write it as equality because I'm univalent. Okay, so so now, and maybe, okay, let me just remind you that sometimes things are good. So with diagonals, this tensor product coincides with the Cartesian product, but we always have this monoidal. And so we're going to consider, CCAT, which is the category of cubical categories. Right, so categories enriched over this monoidal category. Right, so we are enriching in this geometric product rather than in the Cartesian product, if the two don't coincide. And so what I would like to argue now is that the construction of the homotopy coherent nerve is most naturally seen as a construction defined on this category. So my goal, if you will, my goal is construct the homotopy coherent nerve functor, homotopy coherent nerve functor from CCAT to simplicial sets. Right, so I'm not claiming that I'm going into cubical sets. I'm not replacing simplicial sets everywhere with cubical sets. Instead, I'm saying certain constructions are actually constructions cubical to simplicial, and that's their natural way of existing. Okay, so how am I going to do that? Well, I'm going to play the usual game, namely, I'm going to just home out of certain co-simplicial object, which I'll denote Cn into C, and that will give me my my right adjunct. So what I want to do next is I want to explain how to construct this this Cn. So what's Cn? Okay, well, if you ask, I'll tell you. So it's a category, so, well, it's a cubical category, so it has a collection of objects, and the objects will be kind of what you would expect. And then the morphisms, I'm not going to lie to you, also will be what you would expect. So maps, I'm going to say Cn from I to j, I'll define it to be the representable, this one, and specifically, if I can allow myself some, what do you call it? Notational leeway, I'm going to say that these are subsets of the set from I to j that contain both endpoints. Okay, cool. So the next thing I need to explain to you is, I guess, the composition. And the composition will be explained by, well, if you look at the second point of view on like this maybe informal viewpoint, then I want to say that the composition is just the union of subsets. And so let's try to write it formally. I don't know, occasionally one may want to write something formally. So I get Cn, no, Jk, and I want to write something to Cn Ik. And so, okay, what the hell is this thing? This is j minus I minus 1 cube. This is k minus j minus 1 cube, okay? And I tensor them, and I should get a map into k minus I minus minus 1 cube, okay? That is fantastic. So now, what the hell is this? Well, if you believe in, something should cancel. J will cancel. And so I'm going to get k minus I minus 2. And so this map will be a face map. And which face map will it be? Well, there's only one choice, namely j minus I 1. If you contemplate for a second, what happens in this case of a union of two subsets is that I will have one subset that includes j, another subset that includes j. So I really want to make sure that j is in my subset. And then if I count to j, but I start at j minus I minus 1, or at I, or something like that, I need to count to j minus I in order to get to j. If you think for a second what this union of subsets does, that's exactly the phase that you're including. So that's great. This composition, identity, identity, I should say. Identity is clear because you may also wonder what the hell is this thing? Well, I'm just going to say that this is the same as this. I'm not giving you many choices right there. Okay, so next, let's think for a second about what the hell did we just construct, right? So I have some explaining to do. The first thing is I need to tell you why that is a co-simplicial object. And can I even be agnostic and get my co-simplicial object? Or do I need to like already denounce certain religions? The answer will be revealed soon. However, before that, let's just see that what we constructed really makes sense. So let's just, as in when I start humming out of it, I'm really gonna get things that I expect to get. So when I take C naught, well, I'm gonna get just a point. When I take C1, so the zero simplices of homotopy coherent net will be exactly the objects. Now, the one simplices will be a pair of objects, and then there will be just zero cube of maps, so just a single zero cube in the mapping space. Okay, let's look at C2. Well, in this case, I'm not gonna get this. I'm gonna get this instead, 0, 1, 2, and I'm gonna get these maps, this map, and also this map. Right. So what are the mapping spaces I'm expected to see? So between any two consecutive things, I'm expecting to see just a single arrow, which is the zero cube in this thing, and then in the mapping space from 0 to 2, I'm expecting to see an interval. Right? I'm expecting to see 2 minus 0 minus 1 cube, and 2 minus 0 minus 1 is 1. Okay. Okay, and so I'm getting this kind of object here, and I'm drawing it in this direction because that's how I think of inclusion of simplicial, of process, right? Like the thing on the bottom represents the subset 0, 2, and the thing on the top represents stopping at 1. So I believe the containment of subsets is this way rather than the other way around. Therefore, the arrow should go towards the composite. So now let me just tell you C3, and then I promise I'll shut up on, like, I'm not gonna do C4, but I think there's some value in doing C3, so I'm gonna do that. You can, you're gonna get those 0, 1, 2, 3 as objects. And then you're gonna get a map between any two of those. And for any triple, I understand already the mapping space, but the only thing I need to understand is still what is C3 from 0 to 3, right? And so I'm expecting to see a 2 cube there, and indeed I'm gonna see a 2 cube in which I have a path. I can go from, sorry, you know what? I'm just gonna draw this. So I'm gonna have 0, 1, 2, 3. I have these things, and then I also have these things. And so now I can try to do all different paths. So I can go from 0 to 3 directly, but I can also use one of the homotopies to go to 0, 1, 3, or I can use the other homotopy to go to 0, 2, 3. And I can then use the remaining homotopy to go to 0, 1, 2, 3. And this is exactly the 2 cube I'm seeing here, and this is exactly the poset I was expecting to see. Okay, great. So now that we understood that, so this really captures homotopy coherence. And if you ever did the pictures for the ordinary, ever went through the pictures for the ordinary homotopy coherent nerve functor, they look exactly like that, except they are triangulated. Okay, cool. But why am I talking about that? Well, so what I would like to do is extend C to a co-simplicial object. So object, and how can I do that? Well, you'll have to believe me that certain things are just true, but certain other things require some thought. So in particular, I would like to know, what am I supposed to do on this map? I would like to know, this is my, I'm going to say middle degeneracy. So I guess sigma 1. So that's the one that repeats 1, 3, 2, 1, 0. And this is 2, 1, 0. Okay, so I'm just going to draw that 0 goes to 0. 3 goes to 2. And 1 and 2 go to 1. Okay. So why am I making such a big deal out of this? Well, funny you should ask. Well, now let's try to draw the analogous map, C3 to C2. Okay. So, so this is something like C of sigma 1. And so let's look in particular at the mapping space from 0 to 3. And so in this mapping space, well, I just told you what it is. So I have this square here. Sorry, I need to slightly revise my picture. Actually, I think I have this magic trick for doing that. Don't you just love notability? Well, I do. So I'm gonna do this. I'm gonna do 0, 3, 0, 1, 3, 0, no, 0, 2, 3, 0, 1, 2, 3. Okay, and now here I go to, I'm going to go to the mapping space from 0 to 2. So remember that this mapping space was 0, 2, 0, 1, 2. Okay, cool. So now let's see what's going to happen. Well, I know that 0, 1, 2, 3, or this fellow definitely goes here, right? 0 goes to 0, 3 goes to 2. So this goes here. But now both 1 and 2 go to 1. Therefore, maybe I should have made a bigger thing. This thing goes here. I don't know why, but I somehow didn't draw this arrow, right? In the picture over here, both 1 and 2 go to 1. Therefore, those three things go to 0, 1, 2. If I didn't mess anything up. But now, what is this map? If you look at that cubically, this map is exactly let's call it this. This is exactly max. This is exactly the max connection. So the conclusion that I think is important to see is conclusion of this rather long and boring analysis is that need max connections to define the homotopy coherent nerve. Okay, so this is I think last time we had this discussion about our connections, like our connections just like one of those things that rich people get once they run out of important things to get, and the answer is no. Homotopy coherent nerve is the basic right, and we need connections for that. So this is not a privilege, this is really a right. Okay. I would like to state one more thing before we take a break. Or actually, I'd like to prove one more thing. But I need to state one more thing before we do that. So I'm just going to say to the homotopy coherent nerve adjunction, homotopy coherent nerve. Well, it works. So we just play the usual game, right? So we have delta, it has a functor, the C that we constructed into cubical categories. We embed that into simplicial sets. And now we're gonna obtain a left-hand extension and the homing out functor. There is an adjunction and that's gonna be an homotopy. And one other thing that you can observe is that you may have seen the other homotopy coherent nerve functor from simplicial categories to simplicial sets. Well, the observation is not that you saw it at some point. That's not quite what I wanted to say. But you may notice that simplicial categories have a functor into cubical categories, which is this right adjoint to triangulation. And you can then post-compose with our homotopy coherent nerve functor. And the composite here is exactly the usual homotopy coherent nerve. And the easiest way to see that is, well, how did we obtain? So you want to show that two right adjoints are not really isomorphic, I suppose. So you just switch the question to left adjoint. But now these are left adjoint on simplicial sets, so you just check on representables. But then all you need to do, and I apologize for scrolling now, but all you need to do is to notice that the mapping space in simplicial sets is exactly the triangulation of the mapping space I gave here. So what I did is I broke the construction of the homotopy coherent nerve into two, what I'm going to say is two simpler pieces. One that deals with kind of homotopy coherence, and the other that deals with triangulation, right? So I'm getting a simpler construction. Okay, but that's not what I wanted to say. I wanted to say, and I think it's good to get it in before we break for anything really, is if C is locally con, then the homotopy coherent nerve of C is a quasi-category. Okay, so first, let me remind you, locally con means that, well, it's something very simple, right? So CXY is con, is a con complex for all XY. And what that means is you have fillers for all. Oh, I'll have a comment about that as well. But yeah, you have fillers for all things of that form. Maybe I'll write it as that. Right, so this is the analogous count condition, analogous condition to count condition in simplicial sets. Okay, and so I'm going to prove this thing, and the proof is completely analogous to the proof that you saw for simplicial sets, in case you ever read the proof that the homotopy coherent nerve functor is the right adjoint. Sorry, it's not the right adjoint, it's the right Coulomb functor. I think it's not a big theorem that it's a right adjoint. Okay, so well, let's consider a horn to be filled. Like that. So this is a horn in the homotopy coherent nerve of C. Let's call it F. And I'm looking for a filler like that. Well, I do the usual trick. And I switch it to this into C, and I'm going to call that F as well. And now what that comes down to is a lifting problem of that form, if I remember my indices correctly. I think I wrote them somewhere, but no, I did not. Okay, so I think once you start unwinding, that's what you're going to see. This is going to happen in F0, F of 0, F of 1. But now we're using the local harness, and so we're done. So before I move on, I'm just going to note, and I'll start with that in a second, is that we only need half of count conditions, right? And this happens here. Somehow I assumed things for arbitrary epsilon over the top, but now I only used half of them. So maybe I'll start the next part by explaining how the hell is that possible. Okay, so I'll break here.
Could I ask a couple of questions?
Oh, absolutely, yeah.
So the first question is Gothic C a cofibrant, really cofibrant, cosimplicial cubical category?
Yeah. The thing is that we have a model structure on. Well, I haven't said anything about CCAT as a model category, right?
I know.
But yeah, and
but I can imagine. Let's say I'm that's part of the question. Yes.
I mean, you don't need a model as if you're interested in sort of reedy monomorphic as opposed to reedy cofibrant. You can talk about this previous to developing a model structure. And so I interpreted the Gothic C that Ezra mentioned as the one indexed by delta. So that the top factor, the thing from delta into cubical cats, and that is reedy monomorphic, and it's pretty easy to see because for diagrams of shape delta, there's a pretty simple condition to identify when a cosimplicial object is reedy monomorphic, and if you know what that condition is, you can just check.
Well, yeah, but for categories, we also have some operations. So cofibrancy will require freeness, but on the other hand, we can't go in circles. So because it's a post set, it's like a post set. Then it should be believable that sort of combination of those two ideas will get it. I was just checking, if you like, confirming that.
So there is a model structure on CCAT, and I think next week Brandon Doherty will speak about this.
Yeah.
And
right.
I believe this is a cofibrant. Yeah, I mean, like you'd expect the same property of it as you have for simplicial categories.
Exactly.
This is a cofibrant replacement or resolution of the strict
point
one.
of this exactly.
Right.
Yeah.
So So
which is somehow, is it fair to say that straightening is the study of cofibrant resolutions of the strict cosimplicial category? Delta? I'm just going to suggest.
Well, that's certainly a way of viewing. I'm not sure I don't know if anyone would like to contribute to that point of view. I haven't thought about it this way. Yeah,
I mean, you could say like, homotopy coherent diagrams are some sort of cofibrant resolution of strictly commutative diagrams.
Yeah. Okay. Yeah.
And that one such is as good as another somehow. I don't.
Sure.
Okay. Yeah. Could you scroll to the bottom? I had a second question. Is it this half? Could that be also analogous to taking right fibrant C in the simplicial
so I guess
versus left?
So that's what I wanted to start with.
Oh, okay. Yeah. Sorry. I'm getting ahead of you. Okay.
No. I mean, like when the audience is asking questions like that, you know that people still somehow follow you. And
well, I'm trying.
Well, actually, it's worse than that. It's almost worse than that because it's not that people follow me; people are ahead of me. So I really need to make the second half incomprehensible if I want to retain any.
But it's also revealing what right
in the community.
Yeah. But I think it's also fair to say that it reveals what right and left mean, because it's a bit puzzling that top and bottom are the secret, what's secretly going on behind right and left, maybe. Yeah. Okay, thanks.
Yeah, okay. I think, maybe what I'm thinking is why don't we pick up on that point after the second part, because I think then I may have a little bit more to say about certain things. Just now I would, I kind of, in my head I'm kind of trying to think, how do I answer this question by saying something but also not saying anything? So
no need. Let's wait till the end of the second talk. Yeah. How long is the break?
I don't know. Oh crap. Should we say 5 minutes? Unless there are questions. I know what. I'll just have to decide maybe. Maybe not. Okay. Okay. Maybe let's take a 5-minute break. It's 2 p.m. Pacific, according to this thing in the left top corner of my screen. So let's resume at 5. Oh, sorry. At 2:05. It's yeah. Okay. So I'll stop the recording. Folks, we'll be right back. Okay. So welcome after the break, everyone. And yeah, I'm gonna pick up where I left off. And so yeah, before the break, we noticed that for this main theorem, the homotopy coherent nerve of something is a quasi-category if half of the count conditions are satisfied. Well, there's a simple exercise, namely, if you're half con, then you're all con. So what I mean by that is that if you have fillers for all of those guys, I0, or for all of those guys, I1, then you have fillers for both. And what I would say is perhaps, yeah, like this has to do, as Ezra noticed, with the fact that in simplicial sets, if you're a quasi-category, and in addition you have the filler for one of the two outer horns, then you are actually a con-complex. You don't need to verify that both of the lambda n and lambda n0, one of them is sufficient. And the thing is that in cubical sets, if you think about open boxes, which ones are inner and which ones are outer, all of them are outer, right? So instead of like n-1 inner and then 2 outer, you get 2n outer. And this is kind of an interesting point when it comes to constructing the analog of this Royal model structure, which is something that Brandon Doherty will speak about on Wednesday. Okay, so that was one comment. Another comment I wanted to make is that you need to, I realized that now I'm using the same abbreviation for exercise and example. Right, so the previous one is an exercise in combinatorics, and this one is an example. So if I prove this theorem, like what are some examples? What are some locally con cubical cats? Cubical cats. Okay, well, there's the category of con, well, of con complexes, but that actually wouldn't work. Yeah, so Alex says that, yeah, this exercise explains something about Kant's original definition, but yeah, let me finish this thought real quick, that Kant is a cubical category of what I'm going to call universal, let me not abbreviate it, universal Kant complexes. So we know what the Kant complex is, and now X is a universal Kant complex. Universal Kant complex if, well, that's a definition, so just single F is enough. If for all K, X to the power of K is Kant. And so you can say, well, how stupid is that? Isn't when you exponentiate into a Kahn complex, then you should get a Kahn complex. Like we know that from simplicial sets. And so a remark is that if your category is ready and you can do skeletal induction, you can exactly repeat this argument that shows that exponentiating into Kahn gives you Kahn. But if you are not ready, then you can't. Universal Kahn, so in the ready case, universal Kahn is Kahn, but without readiness, you need to impose a stronger condition. And so let me give you an example of an example. Nonetheless, so if X, a simplicial set, is a Kahn complex, so Kahn complex in a sense of simplicial sets, then UX is a universal Kahn complex. So this is easy to see. This is just adjointness. Okay, excellent. So I think that's all I wanted to say about. And let me just point out that recovers the usual fact. Like if you put all of this together, that recovers the usual fact that the homotopy coherent, the simplicial homotopy coherent nerve of the category of simplicial Kahn complexes is a quasi-category, for instance. Okay, so next I want to talk about straightening. Yeah, what's straightening? Well, that's a good question, and the answer is I don't really know. So to me, straightening is difficult. And what I'm gonna say is that to me, what's easy is unstraightening. So what I'm gonna do is I'm gonna actually explain unstraightening, and I'll say very little about straightening. And I think this is the right way to view things. So what do we do? Also, what I want to construct is an adjunction. It goes from slice of simplicial sets over some fixed simplicial set S. So the left adjoint will go to what you can call cubical sets to the power CS, but that can alternatively be seen as the homotopy coherent nerve of the category of cubical sets to the power of S. Oh, and now I have very little space for the right adjoint, which I'll denote as this. Okay, so I'm going to denote it as an integral because that's how I want to think about it. I want to think about this as the Grothendieck construction, right? Or the category of elements construction, which is sometimes denoted by the integral. Okay, so how am I going to construct it? Yeah, so I'm just going to say we will focus on integral of S rather than QS. Q will be important later on, but for now I want to talk about unstraightening, which is easier, right? So so great. So before I do that, I wanna solve like a very simple and intuitive problem, maybe. So here is a simple problem. Simple problem is given a map F from delta n to the homotopy coherent nerve of cubical sets, construct its set of sections. Now that is a ridiculous statement. Absolutely ridiculous. like, what does it even mean? Like, when I talk about sections, I obviously don't mean set of sections of F, like as a map of simplicial sets. I think then there may be some disappointment, given that the delta n is kind of small and the homotopy coherent nerve is depending on all cubical sets is pretty enormous. So what I mean is, well, I'm just going to tell you in examples what I mean. So for n equal to 0, a map F like that is exactly a map from n of C set. So what that corresponds to is simply choosing a single cubical set. And what should be a section of that? Well, it should just be a point in this cubical set. So sections of F is nothing else, but let's say x naught, right? The 0 cubes of the only cubical set I get there. Okay, so far so good. Okay. Next, let's look at delta 1 going into this. Now, what data does that correspond to? Well, it corresponds to choosing 2 cubical sets, x0 and x1, along with a map f01 going from x0 to x2. Well, we know already that the section of a single cubical set should just be an element. So I'm going to draw it like that. X0 here and x1 here. And here I'm also getting f01 of x0. And so if I was kind of trying to take strict sections, I would just require that those 2 elements of x1 are equal. But that's not what I'm interested in. I'm interested in taking a 1 simplex here, which I'm going to, sorry, one, what do you call them? 1 cube. 1 cube. So I'm going to say that a section of such an F consists of a triple of data, x0, x1, well, a triple, no, wait. A triple, I said triple was right, there's no x2. And then P01, okay, as indicated. Okay, now you may have moral objections to the direction of this P, but I'm going to convince you in a minute that you shouldn't. That my morality is actually, at least in that regard, fair. I don't want to jump to too strong conclusions here. Okay. So now let's do the last example. After that, I'll give you the general formula, but I just want to do one more example. So what the hell does this data correspond to? Well, I should get 3 cubical sets, x0, x1, and perhaps x2. And then I should get f01, f12, and f02. And then I'm going to have a homotopy, let's call it alpha 012. All right, between those. That's exactly what the what the 2 simplex in the homotopy coherent nerve is when you follow the adjunction. So we already know what to do for all the data in dimension 0 and 1. So I need to give myself x0, x1, and x2, right? That just comes to me from the fact that I have those gadgets. Next, I look at what the maps tell me. And the maps tell me that I need to get P01 over here. And here I'm going to get F02 of x0. And I'm going to get what? I'm also going to get f12 of x1 and f01, f12 of, no, something's wrong. Oh yeah, sorry. Let's try that again. f12 of f01 of x naught. Okay. And so let's look at what I get. So, so what I'm going to get is P12 over here. I'm also going to get P02 over here. Now, this thing will be F12 of P01. No, yes, wait. Yes, that's correct. And finally, this is alpha 0, 1, 2. And what I'm going to ask for a section is that there will be a theta 0, 1, 2 that that gives me coherence in this way. And so a section of that family will consist of like the 7 tuple kind of thing. Okay. So now the question is, okay, so now let's make it general, arbitrary. And so for f from delta n into this thing, oh my God. I think this is something like when you do the page thing. Yeah, okay, sorry. I cannot display too much and write too close to this. I'm just gonna define sections of F to be a set of pairs. Oh, sorry, no, that's I'm getting ahead of myself. I'm gonna define it to be G from delta 1 plus n into the homotopy coherent nerve of cubical sets, such that G of 0 is the terminal object, and G restricted to delta 1 to 1 plus n is equal to F. Okay? So let me show you that recovers in low examples exactly what I wanted it to recover. So here, extending the thing to from delta naught to delta 1 would just give me a thing like that and a thing like that. And what is a 0 cube in x naught is exactly a map from the abstract 0 cube to x naught. Now let's look at this thing. I put cube naught here, and I add those maps, and I also add this homotopy over here. So now a triangle like that corresponds to choosing a 0 cube in x naught, which is little x naught, a 0 cube in x1 by the second map, which is little x1, and then the homotopy right here gives me my path. And the fact that I'm orienting my homotopies towards the composite tells me that this should really go from x1 to f01 of x naught. Okay, and you can play this game in higher dimensions, and so this really recovers like this thing in low dimensions. Okay, great. So
I could think of this perhaps as being like a cone or a homotopy coherent cone over the diagram F with vertex the 0 square, I guess, 0 cube.
Exactly. Well, yeah. So there's the left-right adjoint thing. So I described for you the right adjoint right now, and so let me describe the left adjoint. And I think like this definition, this intuition will become clear once we instantiate it with S equal to the single, yeah. Okay. So that's great. So now I'm going to say, like now we're doing great. So what do I want to say? Ah, yes. So now I want to define this, and I want to define that. Sorry, I'm taking jump, not X, F. So F here is a map now from S to the homotopy coherent nerve of cubical sets. And I'm going to define it at level n by saying that the elements will be an n simplex in S along with an element in sections Fs like that. Okay, so I know what to do on representable, so I just pull back F to a representable. And so this comes with a natural map to. So this is exactly, if you think about it, this is exactly the category of elements. If I view S as some infinity category and I go to the infinity category of infinity groupoids, or sets, if you will, this is exactly the category of elements. And so this is the construction of unstraightening, and the theorem is this functor from here to some partial sets over S. So by construction, this integral sub S admits a natural map to S, which just projects away the second component. This admits a left adjoint. A left adjoint. And so the proof, well, the proof is now construct straightening. So construct straightening. Given a map, let's call it P maybe, X to S, we do the only thing we could possibly do. So we take X, we embed it into X where this is, let's say, 0 join X. Okay, we take P over here, we take S, we take the push out, let's call that P, and now that gives us a map that I'm going to call Q sub S of P, which will be a map from C, from CS to cubical sets, and this thing is given by Q sub S of P, add some simplex S, let's say this little of S is given by CP0S. Okay. So this is a cubified definition of straightening. But to me, like, I remember reading this definition in higher posterior and not understanding anything, and it took me until I came up with this, that I then reverse engineered the this is it. So I'm just gonna make a remark before moving on that this recovers all notions of straightening. Okay, straightening. Namely, you can get the like the relative version, relative to a map. So in the posterior, you have this thing relative to a map like that, and that's okay. And also a simplicial version. So again, the same story as in the case of the homotopy coherent nerve. Namely, you just pre-post compose by something at the beginning or at the end, like triangulation and its right adjoint, in order to reduce the simplicial case to a cubical case. So there's really nothing going on, and so to me, this is taking something maybe more complicated and breaking it into much simpler pieces. And in fact, like any property of straightening that you can think of, you can prove much more easily in this setting than in the simplicial setting. Because again, you're breaking the difficulty into steps, right? Like there's the true straightening step, and there is the simplicial cubical translation step. And yeah, I think that kind of that's what I genuinely like about it. So you may argue that in the case of the homotopy coherent nerve, maybe that wasn't that much of a gain, like it wasn't that, it's not. But in the case of straightening, I think the construction is involved enough that having a good handle on it is worth. And so the last thing, so this was all from the KV paper. And in the last part of this talk, I would like to talk about the paper, like if Z hasn't fallen asleep, I should talk about like why this thing is actually pretty useful. One of the reasons is that these functors are actually pretty cool. So now let me talk about straightening over the point. Straightening over the point. And maybe I'll emphasize one other thing is, like, if you don't believe me that these functors are useful, these constructions are useful, there's a model structure on cubical sets that Brandon Doherty will explain on Wednesday. And if you didn't have this machinery, I don't think you could compare it with like the cubical Joyal model structure with the Joyal model structure. So I have at least one piece of evidence, very strong piece of evidence, in my opinion, that these constructions are homotopically more natural. I gave you some arguments for why triangulation is a good functor, but I'm now arguing, I think, that from the homotopy theory point of view, this more involved construction of straightening over the point will actually be more beneficial. Okay, cool. So straightening over the point, so that means that we're going to take S equal to delta naught. Actually, before that, are there any questions? Maybe that's a good moment to pause for questions before I move on.
So this definition of straightening here, involving this push out, I can carry it out also without using cubical sets at all. I could use simplicial sets. I could just take the mathfrak C to be the usual homotopy coherent realization. So where are cubical sets sort of really coming in this story?
Well, so in my opinion, the place where they come in is like really you can take two steps at once, but you don't have to, right? Like you can break it into simpler steps. And in the case of the homotopy coherent nerve, we saw that okay, you can break it, and you could maybe make the case that you don't need to break it. Like it was simple enough, it remained simple. Therefore, I kind of wrote it as a composite of two simpler functors, but maybe the original functor wasn't quite as complicated to warrant this decomposition. I would argue that the general notion of straightening is actually fairly complicated to work with. Like that's why we come up with all these intuitions for it. And so, again, I'd argue that like by doing this, you simplify proofs and you can kind of go in the direction of higher category theory that undergraduates can understand.
Yeah, I fully agree that this way of thinking about straightening is very good and much better than how it's presented in higher topos theory. But I was just, you could also carry out that same sort of idea just using simplicial sets, but perhaps it's in the ultimate combinatorics of the thing where cubical sets become a bit easier to think about. Like it's in the combinatorics of this homotopy coherent realization, which is involved in this straightening where cubical sets really.
Yeah, I think that's a fair statement to make, and in fact, like for instance, like maybe to advertise Brandon's talk on Wednesday, in cubicle sets, when you want to talk about mapping spaces, you have a very nice symmetric definition of a mapping space, because cubes are nice and symmetric. Whereas if you want to do the same thing in simplicial sets, you end up with those right-left mapping space that maybe seem less canonical, and maybe again combinatorics of them is more complicated. And so, this straightening construction again lets you approximate between the two cases. And so, yeah, I don't think. I mean, yeah, I think like it's just a matter like you look at proofs in the cubical case, you look at the proofs in simplicial case, and it's just like an enormous gain in like simplicity and how canonical the proofs are. So I think. I guess what I'm arguing is for general usefulness of category theory, right? Like, I mean, every hater of category theory, and I've come across many in my life, will tell you, well, I don't need categories to do that, right? But like, yeah, of course, but I can do it better with category theory, so I don't want to just give it up. So I think that's what I would that's how I would argue this point. Anyway, let me say something about straightening over the point and unstraightening over the point as well. So when you instantiate these things, well, you're going to get functors Q, and now Q will go from the slice of simplicial sets over the terminal object, which that's like my favorite slice to take of any category. To cubicle or to functors from single object category to cubicle sets. And so you get these two functors. So that's a new adjunction between simplicial and cubicle sets. And it's kind of an amazing adjunction if you think about it. Because so far we only knew one adjunction between simplicial and cubicle sets, like triangulation. So now we get the left adjoint going in the opposite direction. So I'm just going to say here that the intuition is Q is the infinity one inverse of T, right? But working with two left equivalent functors is better than working with left equivalent functor and its adjunct. So now we can, rather than trying to show something about the adjunct, like we have T and Q, we can study their composite rather than study T and U or Q and integral. So that's an extremely useful tool, and without that, we wouldn't be able to compare things to like compare Joyal model structures on simplicial and cubicle sets. Okay, awesome. So let me tell you very quickly what the deal with this thing is. So so you can kind of trace this construction of the straightening over the point, but like let me just tell you the punchline. Once you instantiate the construction I gave you above with s equal to the terminal object, let me tell you the punchline as in how do you construct? Well, so the thing is that this is left. This is a left adjoint with value defined in simplicial sets. So we're gonna just play the usual game. Right? So I'm gonna construct some sort of co-simplicial object in the category of cubical sets, and then I'm gonna do the usual con extension and right adjoint. So that's gonna be Q, and that's gonna be the integral. Okay. So yeah. So how do we recover that? I need to tell you what Qn is. Okay, so this is constructed as a quotient. And here, I'm sorry, I need to move this of the n-dimensional cube. So what I'm going to do is I'm going to take 0 in. I'm going to write this thing. And minus, I suppose I should make it I minus 1 here. Yes, okay. So I have all those different face maps over here, and I'm going to be smashing some things to a point. So I'm going to be smashing things to a point, and I'm going to take the push out here, and that's the definition of Qn. So I have different inclusions here. So this is induced by inclusions partial. I'm going to say I, and then is it 0 or 1? This I actually forgot. Wait, I'm gonna say 1, subject to someone checking combinatorics, right? So these cubes, the cubes that I see here are n-1 dimensional, and so I include them as different faces into the n cube, and then I'm smashing things. So maybe we will actually figure it out what I'm supposed to be doing by me remembering what the drawings are supposed to say. So if I look at Q0, well, that's just going to be delta 0 because there are not that many numbers that are strictly between 0 and 0. And then if I look at Q1, again, between 0 and 1, there are not that many numbers, I mean, natural numbers. So I'm going to get delta 1. So far, so good. And now let's look at Q2. And so now that's the first time when I'm going to have some quotienting, and the drawing associated with that is, oh, sorry, I need to erase that. So in this direction, I'm just going to smash that to a point. So my directions are numbered 1 and 2. And so in direction 1, I'm smashing face 2, 1 to a point. So I wrote the correct thing. I think. In direction 1, no, I'm smashing, yes, I'm smashing the face 1, 1 to a point. Yeah, I think that's what I'm supposed to get. Okay, and then I'm gonna say I have Q3, which is obtained from this thing. Oh, I'm gonna move it like that. And so if my directions are numbered 1, 2, 3, then what I'm going to do is I'm gonna smash this entire face here to a point, and in addition, I'm gonna smash, let's say with this color, this face to an interval. And so if you try to visualize it, you'll see that what I'm getting is exactly something that looks like a tetrahedron. Okay, and so I'm gonna leave that for you to figure out. Okay, so since I still have a little bit of time, I'm just gonna say that Q defines a co-simplicial object in C set, and oh, Emily figured out how. Okay, Emily says I'm going to read it without understanding, and then because I'm bad at reading. Here's how you label the vertices in Qn. Start with the vertices in box N, labeled as binary sequences with N coordinates. Then after the first one appears the sequence, the first one appears in the sequence, replace the other digits by 6. Yeah, exactly. Yeah. Yeah, so every I mean, yeah, we have exactly a statement like that in the paper. So maybe I won't elaborate. Oh, Emily said, Chris, that wasn't the comments for you. I just want to say that I agree. And I just want to say that, yeah, if you want to know more, you have to read the book. You cannot watch the movie. But yeah, we have a statement like that in the paper. So I really recommend reading the book. Okay, so so now I'm gonna tell you what the simplicial operators are that make Qn into a co-simplicial object, and they are, so I need to give you n+1 faces, and the faces are a little bit reversed. So the faces are given like the. I'm gonna get the. Sorry, I need to disable chat maybe for a second. So in order to get co-simplicial maps between QNs, I'm gonna have them descend from certain cubical maps between those delta n's. And so certain cubical maps I'm claiming are survive to the quotient. And this is actually not automatic. And so I'm just going to tell you what these maps are. And I don't want to maybe spend too much time on that, but I'm using that to kind of make another point, just because I want to. So these are, so the face maps of the co-simplicial object are taken from certain face maps of the Q. So some of these face maps don't survive to the quotient, okay? Let's see. And you can actually see, sorry, and I'm gonna say that maps don't survive, well, they were kind of used in the definition of this QN. Like we killed them, so let's say the generacies. And so these are given, and that is a little bit surprising when you do it at first, maybe. So sigma n, so the degeneracy of the cubical set, and then you go with connections of the cubical set. So again, we wouldn't be able to write it if it wasn't for connections. Connections are actually like play a very important role in the construction of Q. So whenever you want to use this factor. So the moral of that story is, for now, we need max connections to write down Okay, but let's say we wrote it down. And so now we want to prove things about it. And I'm going to say for the next 10 minutes, so I'm going to take 10 minutes to finish. I'm going to take less. Okay, for the next 5 minutes. Okay, I'm going to spend 5 minutes figuring out how many minutes I'm going to take, and then I'm going to take 5 minutes to tell you the rest of the story. This is the degeneracy. Oh, sorry, that's the wrong order. Faces plus degeneracies plus connections. So I want to tell you a few theorems from the paper with Zach and Z about it. So the first theorem is that, and that's kind of easy to see. So the co-unit of this adjunction. So this is co-unit. Q integral x to x. Yes, okay, that's good. Is a monomorphism. Okay, so why is that? Well, that's just by definition of this integral. So the integral comes out of those cubes that are degenerate enough to look like simplices. So what the integral does to your cubical set is it picks out the maximal subset that is built out of cubes that are actually simplices. Okay, and then Q embeds it back. So this is why this theorem is true. And this is something that requires a proof in mathematics, but intuitively, I'm just going to say that intuition integral picks out cubes that look like simplices. They're sufficiently degenerate to do that. So the co-unit is a monomorphism. Okay, sweet. Then there's also the unit. Namely, what happens if I start with, let's say, simplicial set, let me make it K, and then I embed it, and then I pick out cubes that look like monomorphisms. Well, this is an isomorphism. Because I built this QK by taking cubes that look like simplices, and then picking out things that look like simplices inside of it as my simplices. So I'm going to get this. So again, this is something that requires a proof, but I mean, and this is like heavy combinatorics. So
Chris, do you know if either of these statements is true for the simplicial straightening over a point? I
don't know.
Because I could believe, I don't know, but I could believe that neither is true. And if that's the case, then this is a definite, A plus for the cubical.
I would imagine, like, at least, I know someone should correct me, but like, at most one of them is. I would say, yeah. Okay. So this is there is this. Okay, and so the conclusion is that Q is a co-reflective embedding of S set into C set. So now think about it for a second, and like, how crazy is that? When you take the full subcategory and you take triangulation, that's a reflector, right? Like for the full subcategory, you have a reflective embedding. For just the max connection, you have a co-reflective embedding. I mean, like, I know, like to me, this is like, wow. Yeah, it's so cool that it's like hard to find words, and it's not just me not knowing English well enough. Okay, I'll conclude with one theorem that's proven in the KLW paper. So I'll just say that any cofibrantly generated model structure on S set in which cofibrations are monomorphisms, so are contained in monos. Can be transferred along this functor integral from C set to S set to give a equivalent model structure. So in particular, comments, the conquilant model structure, these Royal model structures, are examples. Not that I need to explain that to anyone here, but one thing is the problem is that not all objects are cofibrant, right? We're doing right transfer, so we're going to mess up cofibrations bigly, and so we're not going to get nice cofibrations. Not all objects are cofibrant. And maybe there are two things to say. One thing is, like, this is not the end of the story. If you want to hear the punchline, join on Wednesday for Brandon to tell you how to construct a model structure in which cofibrations are precisely the monomorphisms. But the fact that we have such nice functors to arrange the comparison is something that then gives us that lets us prove, we can only compare the model structure in cubical sets and simple sets because we have such a nice, we have two such nice functors. Okay, I want to make a couple of comments, maybe. The first thing is come to Brandon's talk. He will talk about all these like the important model structures, but the Mark model. Ezra asked about straightening at the infinity one level, and I would maybe make a comment in response to that there is a point in having a good model for straightening on the one level, and this what I just said is, I think, to me, a convincing argument for that, right? Like, these functors can be proven to be equivalents, and sometimes, even though maybe we have, we understand T and U on the infinity one level, maybe we don't need another pair of functors like that, but really having a good one categorical model for something also is some gain, and I think this is an important thing here. Okay, and I'll say, okay, at this point, I think I'll just say one thing. So I watched a lot of democratic debates, and I learned that having good ideas is kind of irrelevant. Like when you want to convince people, you need to speak to personal experience. So your good plan for healthcare doesn't matter unless some relative of yours died, and that now proves that you actually care about healthcare. And so I'm just going to say that, of course, none of these theorems matter, are not important, but I had a chance here. Just to quote a typical Democrat now, to me, it's personal. And the reason why it's personal is I had my first conversation about cubicle sets and this work with Vladimir when I was still a graduate student. And the third paper here is written with my first graduate student. And so for me, this is really like seeing how much things have changed is kind of really cool. So I just want to say that all the people that I work here with are really, really awesome. And I'm really grateful for the chance to have met them and have collaborated. Okay, I'm going to end here. Sorry for going way over time.
Any questions? Well, I have one.
Okay. Yeah.
So you're getting this. If you lift this Conquillin model structure along this this integral, I guess was it last time Tim gave us a different model structure on some C sets that also did not have monos projective, but had, like modeled the same thing?
Oh, I think I think this one, the transferred one, is even uglier.
Even uglier. Okay.
Yeah. So I'll give you an example. So like this, like the cofibrant object in the model, the transferred model structure, in the transferred model structure will be built out of QNs, right? Like different QNs, because these are the images of generating cofibrations in the other model, like in the concurrency model structure. So that means that, for instance, this fellow, right, won't be cofibrant. Because every cofibrant object needs to have at least one degenerate edge in all of its two cubes, right? Because Q does. So if you think about it, like it's very, very unnatural. The other thing is, like, let's go back for a second to this monomorphism epsilon. If you take Q integral this thing, this is gonna be this, and just like me after the last breakup, it's empty inside. Because the 2 cube does not survive the degenerate thing, so empty inside. And I think there was something in the chat.
I'm just heckling, Chris. You don't need to read this for the audio. So.
Oh, sorry. Okay, sorry. Okay. Oh. Yeah. Okay.
So I have a question. Is there so part of why this Q is so nice is that it comes from this functor from the simplex category into cubical sets, which in a sense picks out cubical sets that look like simplices. Is there a way of describing the theorems, I guess, slightly above on monomorphisms, on the epsilon is a monomorphism and eta is an isomorphism? Is there a way of describing, of attributing those theorems to properties of that functor Q from delta into cubical sets?
I think that's a great question. So there's a couple of things I would say about it. So if you look at our paper, we have a fairly involved combinatorial argument. And if you look at the last paper, the first paper that Brandon will speak about on Wednesday, there the comparison spans like tens of pages of heavy combinatorics. And I would love to know the abstract reason, it seems to me that there is something deep about combinatorics of simplicial versus cubical, right? And it's something that Ezra and I talked about during like Q&A, I think after your talk, actually, if I remember correctly. Namely, like the join construction for cubical sets and so on. So there is some combinatorial things that to me I don't fully understand that at this point. Like I understand every single step in our building of it. And I think there must be an abstract categorical reason why combinatorics works out. But at this point, I don't know. And I would love for someone to like read these arguments and like, work out some magic, it's in a sense, one of those things like, fillers for, like if you're right fibrant, then you're also left fibrant. So like, you can prove it using an involved combinatorial argument, but if you're Joyal, it's just like, hey, here, boom, adjoint, boom, okay, see? And you don't know what happened, but somehow you proved it. And it was like extremely elegant and beautiful. Now, I kind of feel stupid saying like, hey, Andrea, why don't you now take a look at this and work out your magic here? But I would love for another Royale to kind of do the same thing. But I agree with the sentiment that there needs to be some like abstract reason for that, rather than maybe rather than like combinatorial computation. But that's the best we can do.
And I'll admit that I have some ulterior motive for asking this question, in that I think a similar kind of comparison is going to come up in my Friday talk between cubical and globular omega categories. And I've been trying to see if there's a way of making it even nicer along those lines. So if I can think of something in the next few days, I'll let you know on Friday.
Yeah, so
could I have we finished that topic? Because I wanted to make another crazy remark.
Go for it.
All this talk about connections really, so I didn't know what connections were, until last week, but it reminds me a lot of the book of Boardman and Vogt and their discussion of the W construction for multi-categories, for colored operads. And that has been studied and cast into a simplicial framework by Beggar and Modijk. And so I just want to throw out the suggestion that maybe a sort of common unification of those two stories is ready to go, that there could be some sort of cubical treatment of the colored version of Berger Modag.
That would be awesome. So I guess, yeah, I'll ask you for references by
Sure.
email afterwards, but
Yes.
it's, if that, I mean, that would be really awesome. Like, I mean,
Well,
I would love to, yeah.
yeah. So I think, you know, I invite everybody to try to look at Boardman and Vogt and, you know, locate in it the connections. They have them. Yeah, because their W construction is fundamentally cubical. And somehow what Berger and Modag do is fundamentally forcing that cubical framework into a simplicial framework. Yeah.
Mhm. Awesome. Awesome. Yeah, that's.
Okay, I'll send you the
I
reference.
almost wrote in my notebook, ask Ezra for references, which I realized would be
I'll send
inappropriate
you
for
the,
something that I might be posting somewhere.
yeah, well, so I don't want to delay you from posting your next paper on your webpage. So,
No, that's yeah.
Maybe you
And I could add, I'd be
post it
interested
in
in seeing
chat.
those references in the Slack, if possible.
oh, good plan. That's a much better idea. Yeah.
Thank you.
Well,
Okay. So yeah, I guess that's it, and yeah, we'll see you on Wednesday.